All right, I want to take a look at, we worked on this problem when we were talking about what the zeros of a function are. And I want to take some time to talk about some of the nomenclature, some of the terminology here, okay, as it relates to these polynomial functions. And then we're going to tie that back into the idea of the multiplicity of zeros, okay? So when you take a polynomial function and you factor it down into whatever those factors may be. In this case, we ended up here, right? So this is our function reimagined and factored down into these two binomials. These two factors are what we call linear factors, okay? They're linear factors because they are each involving a first degree variable inside here. It's really x to the first. Okay, so keep in mind that there will be times where we're not dealing with quadratics. There will be times where we have fourth degree polynomials, fifth degree polynomials, and a factor may end up being x squared plus 2. In that case, x squared plus 2 would be a quadratic factor. These are called linear factors. Okay, now what we ended up with from these linear factors were our zeros, right? And when you have a linear factor where there is no leading coefficient in this space, the zero that we get from that linear factor is the opposite of this number. And again, this only applies if there's no leading coefficient. There can't be something in this space. Okay, there's a 1, right? There's a 1 here. So when we write these linear factors, we automatically know that the zeros are x equals 2 and x equals -5. It's the opposite of that number. So when this is a +5, the 0 is a -5. When this is a -2, the 0 is a +2. Okay, these are our zeros, right? Because this factor x plus 5 only shows up once in the factored form, we would say that this has an odd multiplicity because it only shows up once, okay? And because it has odd multiplicity, we know that it crosses the x-axis. So this is what I mean when we say we're drawing this back into the idea of multiplicity of zeros. So this graph, okay, would have an x-intercept at -5 and an x-intercept at +2, and we know it's quadratic, so we know its end behavior, and we know that it crosses, and then we have the y-intercept somewhere down here, right? So we get an idea of what this graph looks like based on these zeros. And the same thing would be true over here for 2. Because this factor only shows up once, right? The exponent here is a 1, we would say this has odd multiplicity and therefore crosses the x-axis. All right. Now, one thing that we need to be comfortable with is taking our zeros and creating these factors backwards. Okay, so let's relate that to this problem. Okay, and let's use the graph as we originally stated it to be. So, if I may, if you haven't seen this video on multiplicity, you should definitely go back and check it out. This is an extension of that idea where we crossed at -7, we crossed at -2, and then when we came back here to 5, we bounced, okay? So in other words, we said that 5 had an even multiplicity. Now, what that means in terms of this function, stay with me, is if one of its zeros is -7, that would mean one of its factors might be x plus 7, okay? Because we just said here that in a linear factor like so, the opposite of the 0 is the number that's in here and vice versa, right? So for x equals -7 as one of the zeros, x plus 7 would be the factor, and we would count that one time. For x minus 2, the factor that we get, the linear factor, might be this. Okay, now there could be a leading coefficient here that I don't know about. It just says it has a positive leading coefficient. Okay, now lastly, we had 5, right? And we said that in order for this end behavior to go up and to the left and up and to the right, then it had to bounce here based on the trends that we saw in these first two zeros. Now, again, we drew this freehand and we said it could do this. This is just one example, but I'm using this to explain what even multiplicity zeros look like in the function itself. So as I'm drawing this function out with its factors, x, if a 0 is 5, the linear factor would be x minus 5. And because it has even multiplicity, because we saw that it bounced here, we would see an exponent. So the multiplicity, when we say even multiplicity, that shows up as an exponent here, okay? So there's different ways to consider what this multiplicity means, right? If I had a function, let's do a different example. If I had a function that was x minus 1 squared and x plus 3, let's say I had a function that factored down into something that looked like this, right? The zeros would be 1 and negative 3, right? If I went to graph this, that would mean my graph intercepts the x-axis at 1 and at negative 3, okay? Now, if I hashed out this entire thing, right, this quantity would end up being x squared minus 2x plus 1, right? And if I drew out this entire thing, right, I'm not going to do the entire thing, but I would have an x cubed, blah, 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 and that x cubed would be the highest degree, and the leading coefficient to this whole thing is positive, so I know the end behavior would have to go like this, right? But these are the only two zeros in the problem. So what happens, right? This even multiplicity of positive 1, because it counts twice, and because even multiplicities bounce off the x-axis, I would know that this graph would come here, bounce off that, and then at some point it would turn back down like this. So it would give me an idea of what this graph looks like. It all comes down to looking at the exponent for these factors, okay? Looking at the leading coefficient and understanding end behavior. So that's how we can use the multiplicity of zeros to determine what a graph might look like, okay? So when we talk about multiplicity, we're talking about, does it bounce or does it cross? And we're looking at the exponent for the binomial that is this linear factor. A lot of terminology here, okay? If you got to watch this again, that's fine. All right, we're using words like linear factor, multiplicity, okay, binomial. All of these terms are very important, and they're going to continue to be used, okay?